This is going to be a mixture of things. This is going to be a little bit of me talking, a little bit of kind of more traditional lecturing, if you like, and then we've got some hands-on exercises. So the first question is, do I need a GPU? The answer is no. If everything works smoothly and it cannot possibly go wrong, then everything will work in the cloud, and I will explain that part a little bit later. But first, we've got some kind of a little bit of talk just to kind of give you some introduction to some of the ideas. So before we kind of start, I just want to kind of understand who you all are in terms of your kind of demand for GPU computing, if you like. So who uses GPUs? Who wants to use GPUs as part of their research? Okay, so there's a bit of overlap there. Who has done any GPU programming before? Okay, wow. So there's quite a few that have done GPU programming. Quite a few that not many more of you that have done that than those that are using GPUs. So perhaps some people are using GPUs and don't even realise with some of your machine learning things. So, okay, right, that's good to know. It's good to bear in mind. So we're going to start then with some context. The context is always a ludicrous graph, isn't it? So like, why do we want to do GPUs? Well, it's about performance, isn't it? And if you kind of think about the marketing perspective of why do you want to use GPUs? Well, you've got that rubbishy old CPU. You want to throw a GPU at it and make it kind of hundreds of times faster, and you can do that with just this one little card that you put in your desktop or your laptop, and off you go. And of course, that's nonsense, because it just doesn't work like that, does it? There are so many reasons why that can't. These are kind of like purely kind of theoretical numbers. So there's some huge assumptions that you have to make around this. So firstly, that your CPU is only kind of using one core. So that may be the case with certain code. You've written really serial code, but there are plenty of good ways to get better performance out of a multi-core CPU than kind of writing really slow serial code. And then this kind of massive number. This is not even a latest GPU. This is just something I had on a slide from a while ago. But yeah, so this massive number of teraflops, floating operations per second is, you know, it's a theoretical number. It's really hard to get that, like, unless you're kind of Google or someone, you know, writing really specialist code for kind of exploiting deep learning. It's really unlikely that you're going to get anywhere near that number. But still, there is this kind of expectation that you're going to get good performance out of a GPU. The reality is, you know, with a naive approach, what happens is someone gets a GPU, they run something through it, and then they go on Stack Overflow and say, well, why is my GPU code going slower than my CPU one? I don't understand. It's not a magic solution, right? You can't just kind of plug a GPU in and expect everything to be faster. There are situations where you can make it faster, and with good understanding of the architecture of the device and how to use it as a tool in your arsenal, you can kind of, you know, you can use them very, very effectively. Part of the challenge is that kind of using a GPU requires some knowledge about the GPU, about the architecture, about why it's different. That's what hopefully I'm going to teach you a bit of today. GPU optimization is not easy. Right? CPU optimization is not easy either, but CPUs are really good at hiding really bad code, right? So and we'll explain a little bit about why that is shortly, but GPUs not so much. Like if you write something that's not going to be efficient on the device, you're going to get found out and it's going to be slow, and you're not going to get anywhere near that theoretical number that we saw at the beginning. If you do it right, though, there are some good benefits. So let's kind of give some explanation then as to some of these architectural differences between CPUs and GPUs. Before we do that, just kind of to understand the ubiquity of parallelism, right? So parallelism is already here. It's slightly odd that we still teach programming using this kind of idea of a serial methodology of writing for loops, because parallelism's everywhere. You know, it's in your phone, it's in your laptop, it's in certainly supercomputers and HPC. And the trend is increasing numbers of kind of simpler, lower power cores. So it's not going to go anywhere. We have to be able to write code that can take advantage of more and more cores, whether that's kind of for local compute or whether it's for high performance computing. And really it's this kind of lower end of the computational pyramid, this kind of desktop use that kind of feeds up to kind of larger supercomputers as well. So, you know, writing efficient kind of many core code for your desktop kind of means that you can kind of migrate things further up that pyramid and kind of exploit them at the supercomputing scale. So who remembers Moore's law then? Yeah, good, we've got some computer scientists here. So Moore's law I always find confusing, right, because it's not really a law, it's an observation. And everyone always thinks about Moore's law as being something to do with performance, and it's not. It's about transistors, right? It's about the doubling of the number of transistors, not anything to do with kind of performance. It so happened that for quite a while, those corresponded quite nicely, so you got this nice doubling of performance, but you know, that's not necessarily kind of true and not necessarily going to hold for forever. So it's a really interesting observation because it keeps being predicted as Moore's law is dead. I've seen so many articles of, well, Moore's law's over, we can't scale down, and then it keeps not dying. And we keep finding clever ways to make things go smaller. So we keep getting this same trend of increasing transistor numbers, even now going down to kind of tiny nanoscale architectures. So where does performance come from then? Well, traditionally, performance came from cranking frequency handle, right? So you just make the chips run faster, yeah? But if you crank the frequency handle, then you've also got to crank another handle to kind of counter that if you want to keep your power steady. So you have to reduce your voltage. But you can't reduce your voltage kind of indefinitely because things get a bit noisy and unpredictable. So either you increase your frequency and increase your power, which is not great because then the energy requirements for cooling become kind of quite significant. So it kind of places a limit on how far you can go, how far you can crank that frequency handle. So despite the fact that it's kind of traditionally come from that, you know, Moore's law said instead that we're going to get more transistors, and Dennard scaling means that, you know, that we can have more transistors within the same power window, but it's not giving us performance, it's not giving us what we need, it's just giving us more transistors. So the way in which we get performance and the way in which you can get performance is put those transistors to good use. And to do that, you have to do clever things with the architectural design. Yeah? So use the transistors more effectively to get better throughput on the devices. So I appreciate this may be kind of common knowledge to some of you, but I'm kind of covering quite a bit of background here. So one way you can do this then is instruction level parallelism. So when you build your CPU or GPU or whatever you're building, you build a more complex pipeline. Right, so rather than having just one instruction being executed, you can have a more complex pipeline where perhaps you're doing like an instruction fetch, an instruction decode, an instruction execute, a memory access, and a register write back. You can kind of overlap all those stages because they're kind of a little bit independent. So it's a bit like a production line, an assembly unit. You've got all these different stages all working and things are flowing through it. And if everything's going well, each of those little units within the production line is being kept busy. It's quite effective. And because you're overlapping those things, you can use those transistors to build those little kind of independent stages, and that means that we're getting kind of more performance effectively because we're keeping them all busy doing useful things. So great, we'll just build really, really complicated CPUs and then we can use the transistors effectively. The problem with that, and this example, by the way, it's an ARM architecture, so it's a really simple pipeline. If you look at a more advanced pipeline, there can be kind of, 20-odd stages of kind of overlapping pipeline stages. So they can get really complicated, and that's why they're quite good at, that's why they're quite good at kind of hiding bad code, because this kind of complexity in the architectural design can overlap all kinds of things that could occur, and it means that you can kind of get reasonably good performance out of quite bad code. But you can have problems, right? So I promise this is the only time I will show any assembly code. And it's really simple assembly code. So we've got two instructions here, an add and a copy, and the problem we have is our copy is dependent on the add. So despite the fact that we have this fantastic production line of things that can happen, we have this stall, right? We have this kind of latency that's going to happen because this stage here can't take place because we have to wait on the previous instruction to finish. Okay, oh, it's a disaster. Now all those nice transistors that we built our lovely complicated chip with, they're all sat around doing nothing, so we've caused a problem. But don't worry, we've got more transistors, we can throw at the problem. So we could build a much more complicated pipeline that would do things like speculative execution, right? We could assume that certain things have happened and go ahead and and build a really complicated pipeline that's going to do all kinds of things. And we can write better compilers. That's going to solve a lot of problems because we can shift dependencies around and find good instructions that we can kind of overlap to keep that assembly line busy. And we can just put really big caches and things to avoid memory dependencies. And that's how we end up with quite a complicated CPU that's quite good at hiding kind of the bad code. So we put all these resources to use to kind of build complex pipelines. You can only do that so far. You can only make it so complicated. Beyond a certain point, you know, even with those transistors, you know, you can't effectively do much more useful things with them. You know, there's always going to be dependencies in your code, and you're not always going to be able to just use transistors to kind of hide that. So, so it kind of, you may have seen this graph before, and it's just kind of reinforcing what I've said, right? So we've seen transistors going up, single thread performance kind of leveling off. That's because frequency is leveling off. But the solution, of course, is to kind of replicate. Yeah, so I missed the point to point out 90s dance music. So I called it the golden era, and it's quite often referred to as the golden era in the 90s because there was this lovely free lunch of kind of you could both crank the handles up and build more complex pipelines, and everything led to good performance. So it's after that you kind of hit this wall of, oh dear, we need to do something different. And the different thing is multiple cores. So you just copy and paste, right? So you've got one core that's quite fit. So we'll just have more of them. If we just have more cores, we're using the transistors effectively, yeah, because we're getting those every year. We're getting double the number. We're using them more effectively. But it comes with a burden, right, doesn't it? It comes with a cost because now we have to write different code. We have to write parallel code. We have to write multi-core code. The more cores we have, you know, the more we need to be able to exploit parallelism. So Amdahl's law is a fantastic way to kind of summarize what the problem of that is. Who's heard of Amdahl's law? A good few of you, excellent. So it effectively says that the theoretical speed up is always limited by the part of the task that cannot benefit from the improvement. So there's a nice little graph that summarizes this here. So if you kind of, if you can only speed up 50% of your code, then the fastest hang on, no, I'm going to get this the wrong way around. Let me look at that and get that right. Yeah, so if you can only speed up kind of 50% of your code, the most that you're going to be able to kind of speed it up is a factor of 4, isn't it? Yeah, so 25% factor of 2. Even with 95% parallel code, so if you've got an opportunity within your code to parallelize 95% of it, you're going to reach this limit when you get to a large number of processes. That means that you're not going to make it any faster. It doesn't matter how many more cores you throw at it. It's going to be limited. And as I said, we're still getting more transistors. We've got multi-core designs. We've got now many core designs. We need to find effective ways to use that are not limited by kind of being only certain parts parallel. Yeah, that's only certain parts of your code being parallel. So it's introducing lots of software constraints. Okay, so so GPUs then are kind of, if you like, an extreme example of the multi-core design. So they rather than kind of build more complicated pipelines, they typically use simpler pipelines, simpler architectural design, and dedicate more of the die space to kind of raw compute. So just add lots of compute cores, slightly smaller caches, simpler pipelines, and leave the problem, if you say, leave the challenge to the programmer, right? You'll have to write really good parallel code that can exploit it all, but if you can, then there's some huge benefits that you can gain from using it. And there's this kind of nice graph that I stole from one of the kind of NVIDIA keynotes, and you see they always put the single-threaded performance, the GPU accelerate, and then we've got this kind of super scaling up here for machine learning, and that's because GPUs are becoming not just kind of very effective at doing kind of compute, but also at kind of with traditional kind of single precision, but also at doing kind of really clever things with machine learning, so using limited kind of precision compute and having things like very specialist tensor cores that can do certain types of compute that are useful only for kind of tensor operations. But see this kind of strange super scaling. because GPUs kind of have this difference in architectural design, they spend more die space on kind of raw compute, if you like, there's an opportunity to use them for HPC. If the problem that you have is to do lots of compute and you can parallelize it, then they can be very, very effective, far more energy efficient and very, very effective. But they're not a CPU, they're very different to a CPU. And the reason that they're kind of different is, you know, they spend more of the die space on compute, and therefore they're more of a high throughput device. CPUs you can think of as being kind of latency focused, GPUs you can think of as being throughput focused. So an example, going back to my assembly line example, if we have an assembly line that, manufactures GPUs, then it could take 8 hours in total to get a GPU all the way through that production line. Yeah, that's the latency. But because there's all these different stages, we can kind of overlap things. We can have 100 GPUs made a day. So that's our bandwidth, that's our throughput. You can emphasize that with a picture of a motorbike and a bus, right? So you think of your CPU as being like your fast latency one kind of motorbike, really good for certain tasks if you need to do it quickly, if you need one person on it, if you need like one task, do it really, really quick. But if you need to move a whole bunch of people, it's not much use on a motorbike, no matter how fast it is, you're better off with a bus, right? High throughput device versus high latency device. So I've already kind of made this point, so I won't dwell on this slide, but if you were to draw a kind of a cartoon abstraction of kind of what the silicon space looks like on a CPU and a GPU, then this is what it would look like. CPUs, as I said, not as much space dedicated to raw compute, lots of control logic and complex pipelining, really big caches. GPUs have all this space dedicated to compute, much smaller control and caches, but yeah. So, what does the GPU look like? What's the GPU architecture look like? So this is from an NVIDIA model of a GPU, and I will justify why I'm going to talk about CUDA and NVIDIA and not some of the other alternatives, which I will kind of cover in a moment. But the reality is that they're all much of a sameness. They use different terminology, but they're basically a similar kind of design in that there's a hierarchy. So you have a device, and it has some kind of broken down compute units. So in NVIDIA world, these are called streaming multiprocessors. In AMD world, they're called compute units. And in Intel, I think they're called, what they call, Chris? Z-cores or something. But there's a hierarchy anyway. And then within each of these, what you'll find is that you've got lots of compute cores. So again, in NVIDIA world, these are called CUDA cores. AMD call them stream processors. I think Intel is XMX matrix of vector cores. You know, I don't know who comes up with these really, but you effectively have this hierarchy where you've got these kind of different kind of collections of compute cores, lots and lots of individual cores within it, and then a little bit of shared memory, schedule dispatcher, some instruction cache and registers. And what happens between different variations, different generations of hardware is some of the parameters change on this, right? So, we get more cores within it, or we're going to increase the schedule dispatch, or it's going to have more shared memory. And it tends to go in ebbs and flows depending on kind of how the rest of the hardware is optimized. But because it's built around this kind of these kind of structural units, it means that you can produce GPUs of different compute capability within the same kind of family, within the same generation. So you can imagine a GPU that goes on my laptop, looks a little bit like this, but then the same generation of GPU, the same kind of architecture, could go in a supercomputer, but be much bigger than this and just have more of these. Yeah. So it's kind of the same idea, just kind of replicated. So when it comes to kind of the different choices that you have, there's loads of things, and it's a little bit like top trumps, right? So you can have like the NVIDIA marketing stuff, and they'll show you all the numbers that you want to see, and then you can look at the kind of the Intel stuff, and they'll pick out some really big numbers, and it's a bit like, well, it's not even Jeremy Clarkson on Top Gear now, is it? It's someone else, but they go, oh, here's this GPU, and it's a really big number, and you should all be really impressed. But the reality is that there's this kind of constant arms race going on of who can kind of outdo each other, and it goes in cycles that generally kind of follow their kind of their different kind of spending kind of patterns, if you like, and then they start doing things like making shiny boxes that look nice on marketing material, and then building big supercomputers, because there's this constant arms race of things. What you find is in the top 500, it goes in cycles as well. So I think last time I did this training, it was difficult to see the kind of the top 10 of the supercomputing 500 without seeing something that wasn't an NVIDIA box. And now there's not so many of them around, but you know, they have new architectures coming out. So they tend to it tends to vary depending on what discounts they can offer people who are building big boxes, I imagine. But they are much of the same in terms of the fundamental architecture. And what I hope to do in this course is, yes, we're going to talk about CUDA, and that is specific to NVIDIA, but that's not what I want you to take away from the course. What I want you to take away is a bit of an understanding about the way that you write code for a many-core device, because what you learn about CUDA will transfer to other architectures and to other languages. Okay. So in terms of how you build an accelerated system, you know, if you're doing that on a laptop or a desktop, it looks a little bit like this. The GPU is separate, typically, from the CPU. Boundaries are becoming a bit more blurred now, but and there's some funky products coming around that kind of embed the two things on a single board with special interconnects. But typically, GPU and CPU are separate. They have their own dedicated memory space, and they will communicate usually via PCIe, or in some supercomputing systems, they have specialist links that will interconnect them that are kind of faster bandwidth, lower latency. Same then when you go to a multi-GPU system, it's the same thing, put more of them in. Each of the GPUs has got its own individual memory. Some clever software things around to make it appear that that's not the case, so you can get things like unified memory that makes the whole address space look like it's shared between CPUs and all the GPUs. That's really nice if you want to support your code, but you know, fundamentally things are going to have to move around the memory subsystem, so it's useful to have an appreciation that they are discrete pieces of memory that things have to move around, rather than writing a piece of code that you expect memory to be in a certain place and then something having to happen in the background. So if you're kind of so inclined, you can get a GPU workstation, you can bang a load of GPUs in it. I wouldn't recommend this. It's going to warm your office up. If you've got a cold office, I guess it's quite nice, but they're pretty power-hungry devices. You're much better finding kind of like an accelerated HPC system, something like a supercomputer, which just takes the idea of what I had presented before. It's not that dissimilar from the workstation, other than what tends to happen is there are specialist GPU products that are for going into HPC systems. They tend to be passively cooled rather than actively cooled, or liquid cooled. And that just means that you can use the data centers kind of systems for cooling, rather than kind of relying on noisy fans and things that sit within kind of things like laptop GPUs and desktops. So I'm not going to dwell a huge amount on high performance computing, but what I do want to kind of point out is some observations. And this is a really nice graph. It's a bit out of date now, but it's a really nice graph anyway. What this is showing is it's showing the kind of the different rates of performance improvement for different components within HPC. And everything goes more slowly than floating point operations. So memory bandwidth, networks, memory latency, network latency, they all go. So what it's showing is that this gulf, this kind of gap between raw floating point performance and everything else is just continuing to get bigger and bigger. What that means is the future, the future of HPC, it means that we're going to get denser nodes. Right? If you want to do more compute, want to do more effective compute, the best way to do it is to avoid those things and have more compute in a big dense node. So avoid kind of having to break off a board, avoid having to go across a network and just have denser. So if you want to write future-proof computing or future-proof code, you have to be able to target many cores, have to be able to target very, very dense amounts of compute that's going to continue to scale in this way. So how do we do it? Well, if you're old school like me, I started programming GPUs before you could program GPUs, or before they wanted you to program GPUs. So this was part of my PhD back in, I'm not going to say when, but it was a while ago. And some clever person, not me, realised that you could kind of misuse graphics cards. So graphics cards typically were not used for doing deep learning back then. You know, graphics cards were used for pushing pixels, making computer games look nice. And it turns out that a pixel is just a collection of numbers, RGBA values and numbers. And if you kind of reprogrammed the shaders, the things that would do kind of the ray tracing calculations or the math calculations, sorry, for computing kind of the output colours, then you could kind of misuse them and do interesting things. So this kind of whole community emerged of general purpose GPU programmers. And it was first time by a chap called Mark Harris, who's now at NVIDIA. I think he runs the CUDA development team. And yeah, so this whole community emerged of people misusing GPUs for doing this type of thing. And NVIDIA really were the first to spot this, first to kind of turn it into a product. And what they did was they came out with CUDA, this language which kind of meant that rather than having to write things in graphics primitives and wrap everything up into kind of textures and think about pixels, think about the kind of the different shader components of a graphics card, what it meant is that you could write C code. You could write kind of plain vanilla C code in a special way, and you could target it straight onto the GPU. So the architecture, the things that were pushing pixels became kind of unified into something that could run general purpose code. Yeah, and that has kind of continued and snowballed, and obviously from where we were there to where we are now, obviously GPUs are a very different thing. There are GPUs that don't even have graphical outputs, GPUs that are used purely for machine learning and for deep learning. And a lot of that has been powered by architectural advances, but then also by kind of software innovations as well, and ways of being able to target them. NVIDIA and CUDA is one which I'm quite a big fan of, but it is by no means the only way, and it is by no means the best way. So there's a really good talk that I would kind of refer people through to kind of get a bit more of an understanding about this. So there's a talk called Shifting Through the Gears by a guy called Jeff Hammond, and it's about the idea of kind of, well, what language do you use to program a GPU? There's so many options now, and to be honest, the landscape's a bit of a mess because there's so many different vendors and so many different languages, and they're not always compatible. There's not a straightforward answer when someone says, well, I want to learn GPUs, but I want it to work everywhere. Like, what should I learn? And there isn't an answer to that, right? There's all kinds of different approaches that you could use. So generally, the easiest way to learn how to use a GPU is to use a library and an API, right? These are great. Abstract the GPU away. You don't even know you're using a GPU. So use PyTorch. There's like one setting you do in your settings file, and then you can use a GPU. All those decades of GPU experience are kind of built into the library, so you don't even need to worry yourself about it. And if that's all you need, GPU, great, that's fine. Yeah. Don't worry, you can stop listening now if that's as far as you want to go. Yeah, but if you want to do a little bit more, if you want to kind of program the GPU yourself or add GPU acceleration to a piece of code that you've written or to another library, then you're going to need to find a way to program it yourself. And the easiest way to kind of do that is perhaps with kind of an accelerated standard language design. And you have this kind of trade-off through here, right, of kind of greater productivity and less technical debt versus kind of the level of control. Yeah, not necessarily performance, because you'd like to think, oh, well, if I've got more control, I've got more performance, but that's not necessarily true. Because if you've got more control, you've probably got to put a lot more into your code to get better performance out of it. But there are obvious scenarios, we'll still win in a moment, where having this kind of ease of use will reach a point where you can't actually go any further. You know, you'll get some good performance, but then you're kind of constrained by the simplicity of the approach. So the simplest approach, accelerated standard language design, really easy to do, but fairly restricted control. Yeah, it doesn't expose you to much of the GPU's architecture. The other approach then that's kind of somewhere in the middle is this idea of incremental portable optimization. So typically using something like directives, so something like OpenMP or OpenACC, gives you a bit more control over things like data movement, how to parallelize, OpenMP gives you some kind of increased portability, you can target different architectures, but it doesn't give you the kind of the total control of the architecture. It doesn't give you access to the kind of the really low-level features of the architecture. To do that, you need kind of like a platform specialization language. So you need something like CUDA. There are some kind of things that fit somewhere between these things, so things like SYCL, which is kind of really closer to an accelerated standard language, but it does give you quite a bit more of control, and things like OpenCL. And to be honest, there are a whole bunch of different things that are out there, but all of them fit somewhere on this kind of spectrum of control and ease of use. Yeah. So we'll start with a really simple one. So I will now teach you standard language parallelism in Fortran. Okay, you ready? Okay, now you know standard language parallelism in Fortran. Congratulations. So it's really easy, right? You add this do concurrent. Yeah, so do concurrent, and now if you use the right compiler, and unfortunately there's only one compiler that will do this, and we'll just gloss over that completely, and hence you see the problem of this complicated landscape of languages, but only the NVIDIA Fortran compiler can do anything useful with this for a GPU. But, you know, you can add parallelism to your code. You know, if this is going to work for whatever problem you have, then that's great. But there are some pretty severe limitations with this. Yeah. The first is that there's a big assumption that this thing here can actually be run concurrently. So guess what happens if it can't? All kinds of bad things happen, right? It's undefined behavior, so the compiler will still try and build it and run it on a GPU, but what actually happens could be absolutely anything. Usually it will either be a seg fault or at least the wrong result. Yeah. But, you know, if you have something that neatly can run concurrently, then this can be a good way of doing it. It's a good way of adding some performance very quickly. It ignores the whole, so you don't have any control over the data movement, you don't have any control over how it's parallelized, so there's a lot of assumption that the compiler can do a good job of you know, implementing this very effectively on the device. In some situations that's going to be true, in others it's not. And unless you know a bit about the architecture, you're probably not going to have a good idea about whether or not that's going to be doing anything effective. In this case, it is quite effective to do that. But yeah. So the directive-based approach, I mentioned about OpenACC and OpenMP. It's not wonderful to see it up on this slide, but you kind of do this by keeping the same code, so you keep a kind of standard for loop, but you add these pragmas. This is quite nice because this can effectively just be ignored if you want to run the code in serial, and it will just continue to run as it did before. So you're kind of keeping your code quite maintainable by adding kind of these directive-based approaches. That was, yeah, sorry, that was C++. Sorry, I'm going to jump between different languages just to really confuse you. Yeah. It is a little bit. Can we maybe put the lights down in the front? Is that all right?
All of these off.
Oh, what do we think? All off? On off? Yeah, we'll have all off, yeah. Yeah, because I do have a few bits where we've got some, that's maybe a bit better. So the other options then when it comes to kind of the platform-specific kind of languages are kind of ROCm and HIP. So this is, so ROCm and HIP are the kind of the AMD alternatives, and they have the advantage of being able to run on multiple GPUs, so being able to run on AMD, but then also have a code path through to NVIDIA devices. It's effectively very, very similar to CUDA. In fact, if you were to write something in CUDA, you could very easily port it to ROCm by just kind of mapping the API calls over to a slightly different name. And it tends to be that ROCm implements a subset of CUDA because it has to obviously be runnable on all of the different devices, so you miss out on perhaps some of the cutting edge features, but it has that benefit of being more portable. And lastly and not least is OpenCL and SYCL. So as I said, they kind of sit somewhere kind of in the middle of that kind of spectrum of control. OpenCL is possibly slightly more control, but it's certainly more complicated to write. It has a very kind of Yeah, there's lots of control that you have, but it's slightly more complicated to write than CUDA. SQL kind of is something that is supported by lots of different vendors, and it is in theory a way to write performance portable code. Whether or not you believe in performance portability is another matter, because obviously you could write code once and deploy it anywhere, but that doesn't necessarily mean it's going to run efficiently everywhere. You may have to tweak it for different architectures, but that's a whole other topic. So why a course on CUDA then? Yeah, so, well, firstly, I had some good CUDA material, which was always a good start. I've been teaching CUDA for quite some time. It's been around for a long while. It's not going to go anywhere. It has really excellent support documentation, and you can run it on consumer stuff, right? So if you've got an NVIDIA GPU in your laptop, you can run it. That's not true of all of the different architectures. It's readily available. It's around everywhere. But the most important point, really, is that CUDA is a good way to introduce people to the idea of the programming many core devices and the relationship between how you do that and the architecture itself. So the implications of the code that you write and how effectively it can run on a GPU device. And if that's what I really want you to take away from this. So I don't care if you go away and never use CUDA again, but I want you to have an appreciation of the code that you write and the implications that it has in terms of, is that going to cause memory to move in a certain way? And have I done that effectively? Yeah. Or has this piece of code, does it map well? Is it concurrent? Can it map well to the GPU architecture? That's the thing that I want you to have an awareness of, because then even if you go back to Fortran do concurrent, you can write more effective loops if you have that kind of understanding of the relationship between code and the device itself. So, in summary, GPUs are quite well suited to parallel tasks. They're high throughput. Accelerators typically not used alone, but used in tandem with a CPU. GPU hardware is kind of constantly evolving. We've got this fantastic arms race of things that keeps kind of things moving forwards. GPU accelerated systems kind of vary from kind of single workstations through to massive HPCs, and there is kind of multiple approaches to GPU computing. Each has got a trade-off, and there's not kind of like a single solution that you could recommend to any one person for any one problem. It really does depend on what your problem is and the way you want to do it. So, that is my kind of introduction to architectures. Whilst I prepare to now kind of move on to the next stage of talking about how you actually program in CUDA, does anybody have any questions? No questions. Okay, either I've done a fantastic job then, and you've all completely understood it, or you're all utterly lost. I hope it's the former. Yeah, Tom.
That's not a question. Are there any similarities between SYCL and HIP and ROCm? Because I thought SYCL was kind of similar, but then I wasn't sure about that.
There are similarities amongst all of them in that the purpose is to program kind of massive data parallelism. Right, and I'm going to talk a bit about the data parallel model when I introduce kind of CUDA, but there's similarity in that respect. Syntactically, they're quite different, you know, in terms of how you go about it, but the general idea is what you want to do is launch a bunch of work to happen in parallel with the same program and different data, and the models all kind of do that, just in slightly different syntactical ways.
And I guess it might should have been more specific. So for you mentioned HIP, you don't have to use say AMD GPUs. You can use an NVIDIA one.
HIP you can compile and go through onto an NVIDIA GPU or an AMD GPU.
And SYCL is also multi-platform. Is that the case, or?
Yes, SYCL is multi-platform. Yeah.
Okay. Yeah. I just couldn't remember if they were all like multi-platform. I think it's only.
In terms of portability, CUDA is one of the worst, right? Yeah, it will only run on NVIDIA stuff, but. Yeah. As I said, the idea is this is a proxy for learning how to program GPUs, and it's available, and yeah. I'm not endorsing it in any way. I'm saying it's
just curious.
Yeah. Okay. Thanks. Any other questions? Okay, right. We shall move on to an introduction to CUDA then. So first of all, we'll talk about the CUDA programming model. So we've said that CPUs, GPUs, separate, discrete things. and that's going to be true of when we write a GPU application. So when we write a piece of GPU code, we're not going to have the GPU do everything, right? It doesn't work like that. We're going to write Chris, you have your arm kind of raised to the point you want to ask something, and
I don't particularly. But we had a late question from online. Can GPUs be used in model parallelism? I think that's speaking specifically about ML applications.
in model, I'm not sure what you mean by model parallelism.
So if your model is too big to fit in the GPU memory of one single device, can you use multiple GPUs to do?
You can, and we're getting into quite kind of advanced GPU kind of topics to explain a really good. I'd probably have to spend another half an hour to give you a really good answer to that. But in effect, yes, if you have a really huge model, that thing that I talked about, that unified memory, is a really nice way of doing that, because you can treat all of the system memory like GPU memory, and it will allow you to kind of address all of that on a single device or on multiple devices. Whether or not that's the best and most efficient use of the GPU is another matter. It probably isn't, but you're probably better off to distribute that model across multiple GPUs and use all of those fancy interconnects that you have between them. But yes, you can definitely distribute across multiple GPUs, and lots of people do. And lots of really good libraries mean that you don't have to necessarily have any understanding of that. So a lot of the deep learning libraries will just do that for you. You just give them the GPUs and they'll just eat them up. Yeah. Okay. I'm wishing I had kept the slide that said deep learn all the things now, but never mind. Okay, so when we program the GPU then, what we're going to do is we're going to write kind of a piece of serial code that's going to act like our control flow, if you like. So that's going to do all of the configuration, the setup, all of the things that we need to prepare to effectively offload a little bit of GPU code. Hopefully the thing that we're going to offload is the really slow part of the problem, right? So we had that description of Amdahl's law. Hopefully what we're looking at is, a really high, as a part of the program that's taking up a huge amount of time, is the part that we're hopefully able to kind of optimize using the GPU. And if that's not the case, then we should probably stop, because if only 2% of our runtime is something that we could put on the GPU, it's just not going to be worth it. So we're looking for problems where we have this sequential program, but there's a decent chunk of it that we can move, a compute-intensive chunk of it that's going to match the programming model and allow us to kind of move that over. So because we're going to have these two separate kind of components, we're going to have kind of our main program code, but then we're also going to have some code that runs specifically on the device. And there's going to be kind of a separation of those things. Hopefully it won't be too disruptive. It's going to be reasonably harmonious between the two. They're going to look similar in terms of how you write the code, but there is going to be this process of, at some stage, something will be compiled for the CPU, and then this totally different architecture, this GPU architecture, the kernel code is going to get compiled and put on the device. And the way that's going to happen is it's going to get moved there and then executed. So what that process looks like then is we have our CPU here, we have our GPU here, we have this little connection between them. First stage we're going to do is we're going to copy data from CPU memory to GPU memory, because remember, GPUs have got separate memory to the CPU, and even if we did this implicitly with unified addressing, it still has to move, right? It still has to go from here to here so that we can process it on the GPU device. So we can do it explicitly, or it can be done implicitly. I'm going to show you the explicit way to do it, because I think it's good to have an awareness of when things move and when you should move them and what the implications are, but you can cheat if you so wish. So we copy data from CPU memory to GPU memory, and then we load the GPU program and execute it. So this is where we are going to effectively do the GPU part. The CPU part's the glue that holds this together. It's going to tell us when to execute that kind of GPU code. And then once it's done, we're going to move that data back, move it back to the CPU. Now, if we are so inclined, we might be able to kind of repeat step 2 over and over again, right? So we might be able to keep it on the device and just keep churning it, on the device. And that would be a really good thing to do, because this is expensive, right? This move of all of your memory from GPU device to CPU device is quite costly. So, we don't want to do that much. What we'd like to do is move our data once, do loads of compute, hopefully like iteratively or just a really big kind of compute problem, and then just move it back at the end for whatever it is that we did it at the end, whatever we want to do with it at the end. Write it to a file, create a graph, I don't know, turn it into a picture. So the way that we go about doing that is we use this idea of kind of stream computing or kind of data parallelism. So if you think about the control flow of something like a for loop, it's a bit like this. You've got all of these data elements, and a for loop, if it's independent, is a really nice example of kind of data parallelism. Yes, if you've not got dependencies between the different kind of loop stages, then what happens is you kind of cycle over all these elements and apply the kind of the same program, so the same bits of code. The idea with the data parallelism is that you kind of break that apart, and instead of doing it through a loop, what you do is you say, right, well, I'm going to write a program, I'm going to write this process, and then I'm just going to apply it to a whole bunch of data at once. So it's the same program applied across different bits of data. Yeah. So remember this diagram from, 15, 20 minutes ago? How do we take then this idea of stream computing, of single program, multiple data, and apply it to this kind of weird hierarchy of things? Well, a nice way to do it is to use another hierarchy as well. So when we execute our code on the device, when we execute like a kernel or a program, it's going to apply, as I said, the same program is going to apply to different pieces of data. The way that we can arrange our data to fit within that nice hardware model is using this hierarchy of a grid of thread blocks. So each thread, effectively within the total grid, represents a single piece of data. So it could be an element within a vector, an element within a matrix, could be a pixel, could be anything you want. How you map it to actual memory is your own, we do that ourselves. But conceptually, what we're going to launch is a whole bunch of different threads in this kind of nice hierarchy. So by doing this, it creates something that can kind of transparently map to GPUs of different characteristics. And what you want to be able to do is run your GPU code on GPUs of different generations and of different compute capabilities. So laptop through supercomputer, you want it to be able to kind of map nicely. So, and this grid of thread blocks allows us to do that. So we cluster threads together into a block, and then we cluster blocks into a grid. And we will express our problem as a grid of thread blocks. And it will either be one-dimensional, two-dimensional, or three-dimensional. It doesn't particularly matter. There are kind of constructs for doing that. But we will express our problem in that way. This way, these individual bits, these individual blocks, these can be mapped individually to the streaming multiprocessors. So we don't break them. We don't break them in half. We don't say, okay, well, this one's too big. Typically, what we do is we have this idea of kind of oversubscription. What we want to do is have far more blocks than there are streaming multiprocessors, and far more threads within each block than there are compute cores within the streaming multiprocessor itself. So we oversubscribe, and behind the scenes some kind of clever things happen, some context switching and things happen, which will mask certain latencies that happen on the device. And I'm going to talk a little bit and go into a bit more detail about that in the Thursday session when we look at kind of how to write slightly more optimized code. I promise it's not too advanced Thursday. It's kind of incremental, but I will explain a bit more about that later. So first thing we need to introduce then in the CUDA language to deal with this idea of a grid of thread blocks is these idea of vector types. So we have these things called a dim3. So it's effectively a bit like a structure in C. We have some very special vector types that are used within the GPU program itself. So when we write our GPU kernel, we have access to these 4 special variables, and these 4 special variables are really useful in locating whereabouts a particular thread exists within the wider context of a block and the wider context of the grid. Yeah, so let's have a little example. So although the coloring is not great, we can see I've marked that this one is slightly different, and we can see from the different values what the implications of that are. So thread IDX is referring to the location of a thread within a block. So it's 0, 1, 2 in the X, and then it's 0, 1 in the Y. And because this is a two-dimensional grid block, it doesn't have a third component, doesn't have a Z. Okay, so, but we can obtain the unique position of that thread within the thread block from that thread IDX thing. So this is going to be important later on, but don't worry, we can come back to it. So block IDX will give the location of a block within the grid, so 0, 1, so it's in 0, 1 in the X and 0 in the Y, so this gives us the block. We can get the block dimension, get the grid dimension, and from that we can calculate, from those four things, we can calculate a unique position either in the X or the Y, and that gives us a unique position within the total grid that we have, and that gives us potentially a unique position to index into memory later. So it means that for a particular thread, we have these things, we can use them to construct a unique position, and that unique position can give us the data that we want, the unique piece of data that constitutes our single program multiple data model. Someone was waving their hand. Jack, yes?
Is there a reason it's 3 dimensions?
Is there a reason that it's 3 dimensions?
Like it's just a repetition of one block, so...
There is nothing that you can do with 3 dimensions that you can't do with 1 dimensions and some modding. Yeah, it's there as a handy construct because quite often people want to use 2-dimensional or 3-dimensional problems. Yeah, but if you have higher dimensionality, you can just do it using like a 1-dimensional grid block. Most examples you'll see will be 1-dimensional, with the exception as if you're doing some image processing, sometimes that 2-dimensional grid block's quite a handy construct to have. Yeah, Casper.
On the topic of dimensionality, does the dimensionality
I'll repeat it back if you want to.
Does the dimensionality of a thread inside the block have to be the same as the dimensionality of the blocks inside the grid?
So does the dimensionality of the thread inside the blocks have to be the same as the dimensionality inside the grid? No, you can do whatever you want. Like you can construct a thread block of whatever dimensionality you want. What you have to be able to do is obviously translate from a running thread. You need to be able to usually find.
I'm not talking about the sizes. I'm talking about the dimensionality. So if I decide that my grid is a 2D,
Yep.
whether my thread blocks has also to be 2D, or whether can I do 1D blocks?
Oh, I see. No, you've either got a 1-dimensional grid. I know, in fact. Oh, that's a good question. I don't know. I don't know why you'd ever do that. So I've never thought about that. But I'll come back to you on that. I'm not sure. It'll come to me in a moment. But yeah, Tom.
You can also basically hack it, because if you have a 3D...
Yes, I know that I can hack it.
The last 2 dimensions are 0, then...
I have to say, this is pretty typical of Casper to want to break the model. That, push it to the extreme and see what you can do. But yeah, there are some... I will come back to that. But yeah, the general idea is what you have is you have a grid of thread blocks, and the construct there is there to help you to index to a unique piece of memory so that you can write this single program multiple data model. Let's stop going hypothetical and let's have an example, right? So we will use that by student halls of residence example, right? So the analogy then is that students arrive at their halls of residence in September, and the rooms are allocated. So we could use Churchill College, I guess, yeah. So everyone's arrived at Churchill College and they all want to get their room. Fortunately, admission rates are down, so I think for legal reasons I have to say this is not the case. Admission numbers are fine. But in this hypothetical situation, admission numbers are down. Only half as many students have turned up as there are rooms. So it's a good idea to spread them out because students are pretty noisy and everything. So we'll spread them out and have a gap between them. So effectively what we can do is we can say, oh, every student can be moved from whatever room they're in to room 2i. So just take your number and times it by 2 so that nobody has a neighbour. Okay, so the serial solution there is, they all form a queue in reception, and our receptionist says, oh, what was your room number? Okay, right, so your new room number is 2. Yeah, okay, and then they go off and they go to their room. It's a slow solution, right, because it's quite serial. We've got a receptionist that's having to do all of that compute and inform them. So instead, what we can do is say, well, actually, the process of generating your number is the same. It's the same program. You've all just got a different piece of data. You've all got a different room number. So what we'll do is we'll write a parallel kernel for it, and we'll use a megaphone and say, everybody check your room number times it by 2. Okay, right, go, done. It's really high bandwidth solution. Everyone computes it at the same time. Yeah. So let's write a GPU program in CUDA to do that. And that's what we're going to do. So first of all, this is what the serial solution looks like. Yeah, so we have a piece of memory result, and then for each unique position, so this is each unique student, what they're going to do is take the original number that they had, times it by 2, and write it out to a result array. N is our number of students. And because this is completely independent, so each execution of this through the loop is independent of any other, we can apply a data parallel model to it, we can apply our megaphone, we can parallelize it using CUDA. So this is what that looks like. It doesn't look too different, right? It looks reasonably similar to the for loop. There's a bit of oddness that needs a bit of explanation, but it's not massively different. We've got the same piece of code, effectively, the same compute that's happening, but there are a couple of things that we've done. So first of all, we've put it into a function. This is a kernel function, so this represents the fact that it is a program that is going to run on the GPU device. This decorator that we had there is a global specifier to indicate that that is the case. So this global goes in front of any function that we want to compile as GPU code. Yeah, so it differentiates it from the CPU code, and it means that it will be built using the GPU instruction set rather than anything that would run on the CPU. So we'll go through that process in a moment. The other thing that we have to do then is we have to translate whatever our configuration was, whatever our grid of thread blocks was, we have to utilize that, yeah, and we have to assume that we can get a unique position so that we can translate that into a unique index for our piece of data, so a unique student ID. Yeah. So for simplicity, what we're going to do in this first example is assume that our grid of thread blocks is really simple. Yeah. Our grid of thread blocks is going to be a single block that makes up the grid. Yeah. And it's going to be one-dimensional. And because it's one-dimensional, all we need to do is look at the thread ID x.x. So the first dimension in the block, because there's only one of them, y is going to be 0 for all of them. So so we can get thread ID x.x, and yeah, that gives us our unique position, and that's it. That's our GPU CUDA halls of residence or example. So any questions about that before we move on to something slightly less contrived? Ben, I'll repeat it back so you don't need the mic.
Thread IDX looks like it's a global variable or it's undefined.
That's a great point. It is one of the 4 special variables that I pointed out in the previous slide that is always available within the kernel code. So there is not a concept of a global variable as such, because this code is going to be, this global specifier means that that's going to be compiled for the device code. It's not going to have access to symbols that exist within the CPU code, so it's kind of separate. Yeah. Yes?
When I write now maybe the same code for CPU and GPU, how I put this this first program and this one together in one code.
So could you combine this with, so could you write it once and deploy it for CPU and GPU? You could, but on the CPU you wouldn't have access to this magical thread ID x.x value yet. What you can do, and I'm going to come to it slightly later, is you can make certain functions, not kernels, because kernels are kind of entry points into the device, but separate callable device functions. You can have them compiled for CPU and for GPU. So what you could do is, in your kernel, just do the indexing and out of thread IDX, and then call a function passing through arguments to it that would be for the GPU, or it could have been compiled for the CPU. And then you would have a slightly different code path in that your CPU code wouldn't call the kernel, it would just create the parameters and call the, yeah. Yes?
Is this the programmer who defines the structure? I mean, the dimension of
the grid of thread blocks.
Yeah.
It is, yeah. We're going to come to that. I have to pick one to show you first. I've picked to show you the device code first. I will show you how this is configured shortly. There is this kind of separation. So I said we keep our CPU code. That does the kind of the configuration. So that's going to specify how the grid of thread blocks is and when we launch our kernel. And then we have the GPU code, which is the actual program that is run over the separate data. It's possible that you could write, if you do a bad job, you could do that badly. So, if we launched a a grid of thread blocks with multiple blocks, then it wouldn't be very effective because our actual kernel code is only using thread IDX, so it's only at most using, you know, an index position from a single part of the total grid. Chris?
On behalf of Trav and H from online, who compliments you on your lecture. So question from online, for the same compiler, GPU and CPU floating point calculations are the same, question mark? I ask this because if they're different, using them together for a big code might impose an error.
So there are standards in floating point operations. So now floating point operations so both of the architectures will meet that kind of floating point standard. So they are effectively the same. Yeah, that wasn't always the case, and there were discrepancies. There are things you can do that will break that. So there are compiler optimizations that you can do on the GPU device, like fastmath, that will mean that you can accumulate errors by not quite being as strict in meeting the standard as perhaps you should. There are other areas of the GPU in which you can get kind of some non-deterministic results, but I'm not going to go into those. But generally, yes, they will meet the same standards in terms of floating point arithmetic. Dom?
I suppose perhaps you're alluding to this, but the one thing to bear in mind, I suppose, is if you start with a sequential CPU code and then you create a data parallel version on the GPU, you might reassociate some floating point operations, which will potentially change the output based on different,
Yes,
even though they're implementing the same standard,
yes,
but
so
reassociation
you can accumulate them in different
may be
ways.
happening. Yeah.
There are also, so I didn't want to go into it too much, but you forced my hand. So there are things like atomic operations that you can do on the device. So say you need communication between these separate things that are happening here. There are things like atomics that you can use to accumulate values, and again, the order in which that accumulation takes place can be non-deterministic. It can vary across hardware versions, so you can accumulate slightly different numbers, and yeah, so and that can lead to some non-determinism. So there are things that you need to be aware of, but yeah. Okay, so you asked the question: who configures it on the host? Like, what's it look like? How do we launch our grid of thread blocks? Well, for our example that we had, it looks a little bit like this. So we're going to use this special dim type, like just exactly the same as the dim type that's used in the device code. So it has an X, Y, and a Z component, and we're going to configure two things. We need to say how many blocks are there per grid and how many threads are there per block. Yeah. So for our really simple example, we had one block and we had one dimension. So it would look like this. Our problem size is n, and then we have a dimensionality of 1. Yeah. Blocks per grid, we have a dimensionality of 1 because there's only one. So this is not indexing, this is dimensionality, so it's 1, not 0. Yeah. Okay. And with that, we can run our kernel. So this is horrible. This is not standard C++. This is one of the things that anyone who is kind of a purist C++ person would probably cringe at, but this is how NVIDIA allow you to launch a kernel. So you have the kernel name, you have these weird triple angle brackets, which are kind of highly unusual, but within it, what you do is you specify blocks per grid and threads per block. So you can either use a dim3 like this, or if it's one-dimensional, you can simply put, so for this example, we could have just put 1 and n, and the other dimensions would have been assumed. And then we pass through any arguments to our kernel. In this case, we pass through something called result. I'll delve into what that is in a moment, but we've assumed that it's a piece of memory that could have been written to on the device. That implies that it has to be a piece of device memory, so we're going to have to come back to that. But in order to launch the kernel, we pass through a piece of memory, blocks per grid, threads per block. That's our configuration. Yeah. And we could launch that kernel with different configurations if we wanted, if our memory was configured differently to allow us to access it in different ways. Yeah. So let's have a different example. Another example, but a different example. Let's consider something simple like a vector addition. Right? It's, yeah, fairly simple thing. So right, okay. So vector addition, very similar to our kind of our halls of residence example. What we have is a kernel code. So because it's a kernel, we write global. There's no return type. Never is with a kernel. You can't return something from a kernel. It wouldn't make sense because you've got multiple multiple pieces of data applying the same program, what single value would you return back if it was multiple instantiations of the program for different data? So you never have a return type. So we are calling our kernel vector add. We have a pointer to float called A, B, and C. So this is a pointer to a piece of memory that holds floats. We are assuming that this is memory on the device again. If it was host memory, then this wouldn't work. If this was a pointer to a piece of host memory, then the GPU wouldn't be able to access it because they're two separate memory subsystems. So what we're going to do, again, we're going to keep things really simple. That's not a minus, that's an equals, but the projector can't quite show that, so you're going to have to take my word for it. What we do here is exactly the same. We've got a single dimensional block. We specify it down here in the host code. It's exactly the same as previously, problem size of n. We're getting a unique index into that single block. And because it's one dimensional, we can just use x to do that. We store that index as I, and then we index into our different vectors to read A and to read B, and then to write to C. We use that unique index. Yeah. So single program, multiple data. The data is coming from the index, and because we have configured our grid block in this way, our problem size maps into ensuring that this value of I is unique for every thread and that we cover everything in the block. Yeah. Any questions? Yes.
What happens maybe when the vector is longer than maybe this block size?
We will cover that. So what happens when the vector is slightly longer than this? We'll come to the edge cases. You will come to them in the hands-on material rather than in the slides, but there's a description of how we deal with that. Of course that would happen because not everything fits neatly in a block, and yeah. So one block's not a good idea. I've already said that we can't split a block across multiple streaming multiprocessors. Blocks go to streaming multiprocessors. We oversubscribe the device. We expect multiple blocks to go to a streaming multiprocessor. It's important that we do that. So having a single block's a terrible idea. We're only going to use a little bit of our GPU, and we're not going to be oversubscribing it. So what we should do is use that hierarchy that's presented to us, that nice hierarchy of a grid of thread blocks. And of course, that's what we're going to do. So we're going to take that same example then. So it doesn't matter whether it's the CUDA, the halls of residence one, or the vector addition one, but we're going to turn it from a single block example to a multi-block example. So the way that we do that then is we pick a number of threads per block. In this case, I've picked 8. Don't pick 8. That's a bad number, but it looks nice on slides. The smallest number you should ever pick is 32, because the number of cores is always a multiple of 32. And I'm going to explain again a bit more on Thursday about why that is, and the idea of warps, but we're not going to do that now. But so 32 is the smallest number you should ever pick. You should probably pick a bigger number than that. Again, I'll explain a bit on Thursday about the significance of that number and how you can pick a good number, because there are things that are kind of relevant to that. But for now, because it fits on the slide and makes a nice diagram, I've picked a value of 8. And obviously our problem size then, we will take the problem size of n and divide it by 8 to give us the number of blocks we need per grid. Yeah, so now we have this kind of nice hierarchy where we have individual thread, have a block of size 8, and now we have n over 8 blocks in total that make up our grid. Yeah? So it's a slightly more complicated grid that we've launched, which means that in our code, in our vector addition code, what we need to do is have some slightly more complicated logic to generate that unique index. Yeah? And that's exactly what we have here. So this line here, if you have a one-dimensional problem and you're launching multiple blocks in a grid, this is pretty much just copy and paste. You'll see this in every CUDA program that's one-dimensional. So what that is doing is it's saying take the thread IDX and then add it to the block IDX times the block dimension. So it is generating a unique position, and you can go through the maths in your head if you want, but it's generating a unique position in the total grid. Just exactly the same as it was before. It'd be no different to having a bigger single thread block and just using the thread IDX. It generates a unique position, and then again we do the computation. So the only change here is that we have slightly more complicated logic for understanding what our index is. Now if we had a two-dimensional grid block, that would be more complicated again. Perhaps what we would generate then is an X and a Y, and if we wanted a unique position into, say, a matrix or an image, what we'd do is take the X and then add it to the Y plus width. So it's a very similar thing. So I have some notes here on block sizes. Thread block sizes cannot be larger than 1 or 2, 4. Okay. I'm not sure about that, actually. I'm not sure that's true. This might be an older slide. But yeah, there are kind of some maximum sizes in terms of how far you can go. The key thing that really you should take from this is block sizes should be divisible by 32. Right, always divisible by 32. Just because of how the GPU architecture is designed, everything's a multiple of 32. And varying the block size will result in different performance characteristics. So if you're not sure about how to pick the right number for that, what you can do is you can just try out different values. Yeah, there are some things which we'll see kind of later as to good approximations of how you can pick a different value. But if you think about what happens with the blocks, multiple blocks go to multiple streaming multiprocessors. Yeah, depending on the size of those blocks, you may fit more of them on or less of them on the actual streaming multiprocessor, depending on the resources that each of those blocks needs to use. And that's usually down to registers or things like specific access to bits of cache. Yeah. And as I said earlier, you can kind of shorthand this without using a dim3. If your problem's one-dimensional, then you can just feed the numbers directly in as within these triple angle brackets. So someone asked the question, can you write host code and device code that will run anywhere? The answer is yes. Do you want this before this bit? Or yeah, okay.
If you go back a couple of slides, where you've defined int I. Thanks.
Yes.
Where you've defined int I, presumably we're going to want to go execute things on entire vectors or entire arrays a lot. Do we have to write that out every time, or has someone wrapped up a nice way of indexing a vector, a 2D array, a 3D array?
No, you write it out every time. You could put it in a macro yourself in C, and it would do that. But it depends how you want to index into your memory. Yeah, I can see why you might want something that does that for you, but that wouldn't necessarily be right for every circumstance. So it's important that you do have this direct control to be able to index into it however you want. Yeah. It would be important if you were, say, taking a Fortran array into C, because your indexing you'd probably want to do quite differently. Okay. I'll skip forward again. Right, can you do a host and device function? Yes, you can. So this is host only. It's just a normal function in C. This is a device function, so this is not a kernel. This device, so device is not the same as global. Yeah, device means that it will be compiled for the device only. It means that a kernel, somewhere in your kernel, or another device function, you can call this function and it will exist as a function on the device. Yeah, so if you wanted to kind of have a simple kernel that then calls a device function, what you could do is also put device host, and this will say, well, actually build it for, so run this through both compilers and generate a CPU version and a GPU version. Yeah. Okay, so we're going to have to pick up the pace a little bit. So one of the things that I glossed over was the idea of GPU memory. So in our examples, I said, yes, there will be a piece of memory that we pass through as an argument. One of them will be, it has to be device memory. The way that you do that in CUDA is that you use CUDA malloc. So it's similar to malloc, other than you have to pass through the address of the thing that you want to allocate and a size. So we use the ampersand here to pass through the address of this pointer to float. CUDA malloc will allocate a piece of memory on the device, assign it to A, and it will be this size here. So for all of the problems that we have, we've assumed that had been done. We had a problem size of n, so we have n times size of float. We've assumed that the value we want to store is a floating point value. That could be different, you know, int's the same size, but it could be a double or some other data structure. And because we've allocated memory using CUDA malloc, we have an equivalent which is CUDA free. And that's just the same as free. Yeah. Similarly, if we allocate memory on the device, we need to be able to assign values to the memory on the device. So the way that you would typically do that is by replicating the array or the piece of memory that you would like to have on the device. You'd replicate it in host code, and then what you would do is use something like, oh no, not something like, you do something exactly like CUDA memcopy, where you would specify always the destination first. So CUDA memcopy, what we're going to say is move to a piece of memory on the device from the host, this amount of memory, and we give it this intrinsic that specifies the direction. So CUDA memcopy host to device. So we're saying move everything that's pointed to in this piece of host memory to this piece of device memory, and do it for this size of memory. Yeah. Likewise, when we move it back off the device, we do the opposite. So destination always first, we've got host and device. Size again is the same, and then we say device to host. Yeah. So transfers, as I said at the beginning, are quite slow. You know, it's all got to kind of transfer over PCIe or whatever kind of link architecture is going on there. So what we want to do is minimize memory copies and maximize the amount of compute. So make sure our kernel's doing plenty of work. What we don't want to do is kind of copy, compute, copy back, and constantly kind of we'll spend all our time copying and not getting the advantage out of the GPU. And this is where some of the standard language parallelism can fall down, because it's very easy to write something that parallelizes well on a device, but the cost of moving it there means that you're not going to get a huge amount of benefit, because yes, you've sped up your code, but you've taken time to have to move it there and then to move it back. So this is a little bit hard to see, but we have this in one of the examples, so I'll gloss over it quite quickly, I think. But it is effectively a complete example of the vector addition problem. So we have our global up here. So this is the same kernel as that you saw on the previous slides. We have our program here, so our entry point called main. We have some pointers that will be pointers to memory on the host. We have pointers to memory that will be on the device. And as a nice kind of programming approach, I always tend to kind of prefix that with D underscore, so we know that it's a pointer to the device. There's no difference. A pointer is a pointer. It doesn't matter if it's host or device. It's just its different address space. So there's nothing fundamentally different about these as pointers. They're all just pointers. They're just pointing to different memory subsystems. So if you try and dereference a pointer on the host, or try and dereference a host pointer on the device, it will just, I don't know what you're talking about. Yeah, okay. So we do our CUDA malloc here. So we allocate our device memory. We do some host mallocs here. We assume that there's another function. I haven't included it, but there's a function here that will allocate some random floats to A and B. We don't need to allocate anything to C, because that's going to be where we put our result. We have our memory copy here. So destination first, we're copying from A, this size into device A. Same with B, size into device B, copy host to device. So we've moved all our data to the device. We are going to call the vector addition kernel. So problem size n over threads per block. So we've made the number of threads per block configurable with a macro up here, and then the number of threads per block. So this is threads per block, and then the number of blocks that we need. And then we pass through the device pointers as arguments. At the end, we copy it back, and then we do our freeing up. So it's not very useful as a program, because we're not even printing the result out, but it is a complete example of doing a vector addition. Yeah. Just because it doesn't make much sense to put this anywhere else, it's kind of tagged on at the end. There's a call that you can make called CUDA device synchronize. It's important to note that when we call vector add, it's an asynchronous call. So when we got to this point in our code here, where we say vector add, this is instantaneous, right? So it calls this, and the GPU will then begin an asynchronous process of performing that kernel. The CPU will carry on, right? It will carry on doing things. It will carry on executing instructions, even if that GPU code hasn't finished, until it reaches a point where it needs to synchronize. It just so happens that CUDA memcopy is a blocking call, yeah, so it will force a synchronization. So the CPU will call that, it will get to here, and it will kind of have to wait now until this kernel has finished executing, because it doesn't make much sense to start copying the result back until the kernel's finished. There are ways and clever ways that you can do more asynchronous stuff with different streams, but that's a more advanced topic for another day. But it's important to be aware that it is synchronous, so you can call CUDA device synchronize, which is rather than implicitly waiting for a synchronization. And it will always have an implicit synchronization with the CUDA memcopy. Then, yeah, this is just another way to do it. So it's a nice way if you want to perhaps time your code, you'd have to put a device synchronization in to make sure that you're not just timing the launch, you're actually timing the compute as well. So I've got hiccups. It's okay, we can do this. We've got like 5 minutes. This is perfect. Okay, right. So what happens when you compile your CUDA program? So we're going to compile it using the NVIDIA CUDA compiler, or NVCC. It's pretty much like any other compiler. It's pretty much like GCC. The main thing that's going to happen that's different is some things are going to get processed by the host compiler and some are going to get compiled as device code. And the way that that's going to be separated is by those labels that we saw. So anything that had global in front of it is going to be stripped out by the NVCC, by this kind of pre-processor that goes on. Anything that's host related is going to get compiled into kind of host code. Anything that's got global or device in front of it is going to get compiled into CUDA kernels. Again, it's going to create some binary objects that then will get embedded at the linker stage. And what you can do is there are different kind of, in fact, it's on my next slide. I was wondering whether I wanted to say that or not. But there are different device versions. So different GPUs, as they've got newer, have had different compute capabilities. So you can imagine the GPU I started on kind of many years ago lacks many of the features that a modern GPU does today. There are all kinds of advanced things that you can do. I say even when I started, there were differences in floating point precision. Now there's tons of kind of advanced things that can happen. And the way the compiler kind of accounts for that is this idea of compute versions. So if you say I want to compile for compute version 6, then it will compute for a particular architecture, and the compiler can make certain assumptions and use certain features of the architecture. It's transparent to you as a programmer, but it just means the compiler can use more features and usually target the code slightly better. So newer GPUs have newer compute versions. You can build for multiple versions. So an older compute version, if you build for compute 3.5, which is the default, you can run that on any newer hardware. Yeah, but because it's been compiled for an older architecture, there are certain things that it won't be able to do. Yeah, so it will be lacking perhaps some advanced optimization. What you can do is you can build for a whole bunch at once. So you can put, do I have an example? I don't think I have an example of it here, but I think there is in the handout. You can specify them like this, and you can build for a whole bunch of them, and then it will embed the binaries within the CPU program so that at runtime, depending on what device is available, it will pick the latest compute version and deploy it on that device. Yeah. So, in terms of CUDA, it's a C-like programming language. Yeah. Hopefully there's not too much scary stuff in terms of the C there. There are a few things, if you're not a C programmer or you've not done C programming before, you might be a bit, okay, right, well, tell me more about pointers. Don't worry. In the hands-on material, if that's something you're not sure about, I'm happy to sit and go through that and explain that in a bit more detail. But it's very C-like programming language. There are all kinds of things that you can do with CUDA now that are kind of more C++-y. Typically, the advancements in CUDA have kind of been introduced to make it more accessible as a language, to make it easier to embed GPUs into your code. So things like support for kind of C++ objects is kind of fully there now. I prefer to teach it from the C way because it kind of introduces you to all the ideas and you get that understanding. If you later want to use things like unified memory, it's a good idea to do it, but you at least have an appreciation of the fact that memory has to move and how to do that explicitly. Yeah. And then when it happens implicitly, you can understand why and where and what the implications are. Yeah. So programming GPU requires moving data to and from the device, so separate regions of memory. If we're doing compute on the device, we have to move things to it, have to move things back at the end. Parallel regions are executed using single program, multiple data, using this idea of a kernel. Kernels require high levels of parallelism. We always oversubscribe the device in terms of threads per block and blocks per grid. And host and device code are compiled separately and linked into a single executable. So I'm going to take some questions in a moment if there are any more, but we're going to stop in a moment, and then when we come back, I have prepared a lab exercise that we'll go through and allow you to try some of this stuff out. So in order to do so, I have built a website that will allow you to have access to a cloud instance. Yeah, so there's a description of what that cloud instance is, but the reason I've done this is because obviously I don't expect you to alternate with a GPU. If you did, it probably wouldn't be configured right. If we relied on a high-performance computing system, we'd have to make reservations and all kinds of complicated things. The idea of this website is when you go onto it, if you sign up, so when you first get onto it, so choose to log in and then sign up as a new user, if you use the email address that you registered with for this event, then I have allocated you onto a lab and you'll get a list of labs. I'll show you it when we get back from coffee break. But you can click on a lab, click a button, wait a few minutes, and it will give you a Jupyter notebook with a GPU backend, and yeah, and it will work. Yeah. That's the idea anyway, so okay, thank you very much. Yeah. So I promise I'm not going to do any more talking after the break. I'm going to be walking around and helping people as they kind of have a play with the labs. Chris is going to be doing the same. He's just going to be walking around and answering questions. Tom as well, I think, has offered to perhaps do that, which is great. So if you've got any questions, you can either ask them now, we've got a couple of minutes, or you can wait and ask them individually to one of us as we walk around and you try the exercise.